Unit 3, Forces Supplemental Problems, numbers 1 and 2, with a review of some force diagrams. We may or may not have gotten to that point in class. The first problem that we have is no forces are involved. It's just a good practice problem, a reminder of what we're supposed to be doing. With these, we have the plane turning at 20 degrees. It might be easier to visualize this if we kind of look at it and adjust it a little bit more. We can see that if we kind of adjust the things a little bit here, get that done. With the resultant being at almost what we have, and so we kind of look at when we put it together with the picture, we can see that we need to put in this being what A is our 12 kilometers, and B being 21 kilometers. That if we took that, and we can kind of see where that 20 degrees comes into play now. Now, of that 20 degrees that we can see, I'll use a blue line for the 20 degrees on what I'm talking about with this 20 degree turn. You can see that that little angle right there is a 20 degree angle that they're talking about in the problem, but this angle right here is actually what we need to solve for, and that would be the theta of 160 degrees. From there, it becomes very much a straight law of cosines problem. So we would have r squared is equal to a squared plus b squared minus 2ab cosine of theta inside there. And then it's just a pure substitution of your problems of 12 squared plus 21 squared minus 2 times 12 times 21 times cosine of 160. That's going to get really small in there. Cosine 160. And we'll very quickly go through and do some of the math. 12 squared would be 144. 21 squared would be 441. We add those together to get 585. Technically, the kilometer should have been added in there, but I didn't do that. Obviously, ran out of space to begin with. A negative 2 times 12 times 21 times this cosine of 160 gives us actually a negative number of 473.61 kilometers squared again. Now, because of that, we can see that the two negatives will cancel out, meaning we can add them together and get a total value of 1,058.61 kilometers squared. But that is still equal to the r squared. Now, to get that finished off, that didn't work, we need to take the square root of both sides, and the square root of 1,058.61 kilometers squared. The squares there cancel out, and that becomes just kilometers, giving us a R value of 32.5 kilometers. Again, pretty straightforward, kind of a nice little problem that very nice to get used to. Now this next problem is again another problem that does not revolve any forces, but is definitely a nice review to do. The direction of the picture really shows us the direction of how something is falling off. We have two things with that. We can see that the 58 degrees there is there, and which would give us that angle be 32 would be this angle down there in the red. So we have two angles we can deal with. So we can kind of go with, depending on how we want to approach this problem, or how we want to change, or what angle to use. We know that the V sub I is equal to 6.25 meters per second, and again we can, depending on the triangle, will depend upon which one you want to go with. If you go with a 32, you have to be careful and actually look at how you're going with it. If you go with a negative 32, or you could use 58 in any of these calculations. It is again very similar to a problem that we had seen last unit, where we use the equation V sub x is equal to V sub I times the cosine of theta, and V sub y is equal to V sub I times the sine of theta. And we can then look at both of those, substitute what we need to substitute in. So V sub x, we would have 6.25 meters per second times the cosine. I'm going to use negative 32. You can again 58, 58. I'm sorry, works just as well. But it will. You can't use regular 32 because that will get you the incorrect way. It's based on how the direction is pointing. It might be easier to you just use a 58, but again, it does not matter which one you go with. Sine of, not sine. Sometimes the again sine of a negative 32. Doing based on that, again, the math is pretty straightforward and easy to look at, and so we would actually get a value. And using the negative 32 does kind of have some value to us, in that we see that it has, especially when we get the V sub y value, and we get a 5.3 meters per second in the V sub x direction. That is that horizontal direction, but our V sub y is going down, and using a negative 32 does help and get us that negative 3.3 meters per second that we so desire. And so that's kind of giving us the first two problems that we have. Now with this slide here, we have kind of a setup of what a free body diagram might look at. Any of these forces can happen at any angle, say if it's sliding down a slope, being drug up an incline, anything such as that. Weight is normally looked at as mass times gravity. Without getting in too much involved with the Newton's laws, the normal force of the Earth on the object, and so I just use an O, the normal force of Earth on the object should equal, but opposite, the weight of the object in which you're using. Now the force over with just the F is your frictional force. It's always opposite of the direction in which the push or pull is. So that's friction. And then we have the normal force, and this is usually a push or pull. We might see it as tension, which would give us the pull, so that sometimes you might see it as a capital T for tension. That would be the pulling part of it. Depending on how complex your system is, will depend on how many arrows, what the other parts that would be in there. But for the most part, you should have 3 to 4 different things. If the force is not acting on it, it does not exist. That's one of the things that we'll talk about in a later slide when we're talking about forces and circles. If the force is not there, it does not exist. If there is no acceleration, we know based on the equation of force is equal to mass times acceleration. If acceleration is 0, the force also doesn't exist. But really, this force here that I just circled is actually better termed as the F net, and that is the sum of all the forces involved. So we want to have sum of all the forces that are involved with that when we draw our free body diagrams. We've, in a way, been practicing sometimes these free body diagrams by drawing pictures for what we're doing or what we're seeing happen in a problem. It's just a different way that we're now just being very specific about the forces that are involved. As we kind of close up with this, as the next some of the problems start to deal with forces, and therefore your understanding of the how to draw a free body diagram will become much more useful. Thank you.